Okay, so the last thing I want to talk about in this lecture, so we posed the question when we talked about Levenspiel plots, why FA naught over minus RA might decrease with XA. So if you remember when we talked about Levenspiel plots, so we'll say recall from that lecture. That we drew a Levenspiel plot, which is basically we're saying FA naught divided by RA on this axis and XA on this axis. And the plots we looked at looked like this. So what we're saying here is, in some cases, the Levenspiel trend, FA naught, can have regions where it decreases with X. So why might that be? Why do I have this? What's going on here? And at this point, we now have enough information to be able to answer that question. So if we consider this example, where the rate is equal to a rate constant times concentration to the n, and we'll say n is greater than 0, so n is a positive number. So let's consider here two cases. Let's consider one case, an isothermal case, and one case, let's consider a non-isothermal case, and to make it simple, let's call it an adiabatic case. So in the isothermal case, the temperature doesn't matter. So the temperature is held constant. In that case, the rate is only a function of the concentration. So we'll say no T dependence. So in that case, we have up conversion, we have down concentration. That means we have down rate. And that means up 1 divided by the rate. In the adiabatic case, there is temperature dependence. So T matters. In the adiabatic case, the rate is a function of temperature. So we'll say rate on temperature. So let's consider the case of an exothermic reaction. So in this case, as the conversion goes up, the temperature goes up. So an exothermic reaction gives off heat. So the more that of the species A that reacts, the higher the conversion of A, the more heat that's given off, and thus the temperature goes up. So this is going to increase the rate because it's going to increase the rate constant. Therefore, 1 divided by the rate is going to decrease. So that's what you see when the conversion is low. As the conversion increases, the temperature is going up. That means the rate is going up, and that means 1 divided by the rate is going down. At this minimum here, we've reacted so much A away, so much of species A has reacted away that Ca is very small. When Ca becomes so small, that means that the rate slows down. And when the rate slows down, so does this temperature increase. The rate isn't increasing as much. And then in this region, the rate becomes concentration dominated again. So here we have, on this side, when we have a decreasing regime, here we have a temperature dominated regime. And here we have a concentration dominated. And what happens here, so after this point, Ca is so low that the reaction is barely proceeding. And because the reaction is proceeding so slowly, the temperature is approximately constant. Let's just say temperature so the rate isn't going fast enough to be giving off heat at any appreciable rate. Because of that, the temperature is only changing very minorly. In fact, it resembles a constant temperature reaction, and then we recover this concentration dependent or this concentration dominated behavior.